Everyone knows what a credit card looks like. Some numbers, your signature, a big magic black stripe on the back, and a chip on the front. A chip that's actually a tiny little computer with its own RAM and its own ROM that does a billion things to make sure you're actually you. And it all starts with the circuitry. Say you buy something and you stick your card into the terminal. Immediately, your tiny little computer gets to work. So, zooming in, when those gold contacts on the front meet the spring-loaded pins inside the terminal, that moment of touch will actually deliver just the right amount of electricity to wake up the chip and begin the secure process. Well, it doesn't have a battery, so it relies entirely on the terminal to power up. As soon as it's awake, the card and terminal begin their communication using a standard protocol called ISO 7816. This is how they recognize each other and start the conversation. What you've just activated is called an EMV chip, and it's named after Europay, MasterCard, and Visa, the companies that created the standard back in the 1990s. Inside that little square is a full-blown computer built onto a tiny slice of silicon. It holds microscopic components like transistors, capacitors, and resistors, all arranged to do one job really well, to make sure your payment is safe. And it runs a simple but secure operating system called a Card OS, or COS. It's written in stripped-down languages like C or Java Card and stored permanently in ROM. This software is designed to do just a few things: respond to commands, perform cryptographic calculations, and securely manage data like keys and transaction counters. It's small and usually just 16 to 24 kilobytes of code, but airtight. The chip itself includes a tiny CPU, usually 8-bit or 16-bit, running at just a few megahertz. Compared to your phone or laptop, it's slow, but it doesn't need to be fast. It doesn't have to, at least. Its only mission is security. It executes instructions precisely and predictably, without opening itself up to side-channel attacks or unexpected behavior. Surrounding that processor are 3 types of memory. ROM holds the operating system, and it never changes. EEPROM is where flexible data lives. This is where your card number, the number of times it's been used, maybe some bank-specific settings can be found as well. It typically stores between 16 and 32 kilobytes. Then there's RAM, the smallest of the 3. It's temporary, just enough to handle live operations during a transaction, maybe in just 1 or 2 kilobytes. And it's automatically wiped the second the chip powers down. All of this happens invisibly, behind the scenes. From the outside, it looks like nothing more than a small chip embedded in a plastic card. But inside is a finely tuned, purpose-built computer, working tirelessly to protect every tap, dip, or swipe. Speaking of technology that powers our everyday lives, understanding how these systems work has totally changed the way I look at the world. If you're curious about diving deeper into topics like this, Skillshare is a great place to start. It's an online learning platform with thousands of classes on everything from tech and productivity to photography and design, all taught by real experts. Right now, I'm taking social media content creation in Canva by Maggie Stara, and it's completely changed how I design thumbnails for videos like this one. The lessons are clear, hands-on, and easy to follow at your own pace. Best part? You can actually share your work and get feedback from others, which makes learning way more fun and useful. And hey, the first 500 people to use the link in the description get a whole month of Skillshare completely free. Check it out and start learning something new today. And once it's powered up, the chip initializes and gets ready for the transaction. Modern chips can even handle multiple applications like credit, debit, loyalty rewards, or even transit passes. So the card and terminal first negotiate which application to use based on what's available and what the terminal supports. Then comes the critical part, authentication. The card needs to prove it's legitimate, not a clone or counterfeit. It does this by performing what's called card authentication, using serious cryptography under the hood. Algorithms like triple DES, AES, RSA, and ECC are the common ones, proving to the terminal that the card was issued by a trusted bank and hasn't been tampered with. After authenticating the card, the system moves on to verifying you, the cardholder. This is where you might enter your PIN or provide a signature. But your PIN isn't sent openly across the connection. Instead, the terminal encrypts it before sending it to the card, and the chip can verify whether it's correct without ever learning your actual PIN. With authentication and verification complete, the chip generates something called a transaction cryptogram. Think of it like a one-time use digital signature unique to that particular transaction. This is one of the biggest security advantages of chip cards. The chip generates a brand new code every time you pay. It's called a dynamic CVV or tokenization, and it makes replaying or cloning your transaction practically impossible. Once the cryptogram is created, the terminal sends it, along with the transaction details, to the payment processor. The processor verifies the cryptogram using secret keys stored by your bank, checks your account balance, screens for any signs of fraud, and sends an authorization response back to the terminal. All of this, from insertion to approval, happens in just a few seconds, and has only been happening to what's the chip on the front. And what about the stripe on the back? The black stripe is officially called a magnetic stripe or mag stripe. And it's actually a much older technology. Before chips, we relied on the magnetic stripe. It was invented back in the 1960s by an IBM engineer named Forrest Perry. The mag stripe is made from tiny iron-based magnetic particles embedded in plastic film. It works a lot like a tiny piece of magnetic tape, similar to what's inside cassette tapes or VHS tapes. Each of these particles acts like a mini bar magnet that can be magnetized north or south. It contains 3 tracks of data. Track 1 carries your name, account number, and extra details. Track 2 has your account number, expiration date, and a service code. Track 3 is mostly obsolete now, but it was originally meant for things like updating balances on prepaid cards. So what's happening is that when you swipe your card, a magnetic read head, much like the read head on a tape player, reads the data by detecting the alignment of tiny magnetic particles. The problem is, this data never changes. It's static. If a criminal uses a skimming device to copy your magnetic stripe, they can clone it onto a blank card and use it just like the original. No encryption, no dynamic codes, no authentication. This vulnerability led to an explosion in card fraud, especially in the early 2000s. That's why the world started moving to chip-based transactions. The EMV standard was introduced internationally in the 1990s, but it wasn't until around 2015 that the United States pushed hard for adoption after seeing significant levels of card-present fraud. Today, most countries have phased out magnetic stripe transactions almost entirely. In fact, MasterCard recently announced plans to completely eliminate magnetic stripes on newly issued cards in the coming years. The industry is evolving towards something even faster and safer: contactless payments. Contactless cards use a small antenna embedded alongside the chip to communicate with terminals wirelessly using near-field communication or NFC. Instead of inserting your card, you just tap it. Underneath, the same principles of dynamic cryptography apply. Your card still generates a unique cryptogram for each transaction, protecting you against cloning and replay attacks. Mobile wallets like Apple Pay and Google Pay build on this even further, combining device-specific tokens, biometric authentication, and the same cryptographic protections used in EMV chips. In a way, contactless technology is the natural evolution of everything the chip started, shrinking powerful security into something you barely even notice. Behind every simple tap or swipe is a whole world of engineering and trust, invisible yet vital. A reminder that behind the simplest actions, there's always a deep conversation happening between humans and machines.